Okay, so let's get started again. So there's only one more session, two talks. This is a quantum dynamics session. And so our first speaker is Sarang Gopalakrishnan, and he's going to talk to us about persistent quantum coherence at high temperature.
Thanks very much, Matt. Thanks all the organizers for having me here. It's always nice to be at Rice and see all these familiar faces. So I'm going to talk about something rather surprising that we came across earlier this year while thinking about single particle Green's functions at high temperature in sort of very generic chaotic systems. This work was done by my postdoc, Ewan McCulloch, who only works on problems that have charge conservation, so he's U1. And in collaboration with my student Alex and Kurt von Kaiserlink. Right, Mike already motivated this to some extent, but how much do you need a quantum computer to study quantum dynamics? Yeah, maybe you do need a quantum computer if you want to compute every possible observable, but suppose you only care about the kinds of things that a physicist would ask about, like expectation values, correlation functions, the simple operators, things like that. To what extent, can you just cheap out and do them on your classical device? And this is sort of an analogous question comes up in classical physics. In general, many body dynamical system of interacting objects is chaotic, even if it's, a bunch of like hard spheres bouncing around in a box. Predicting individual trajectories is essentially impossible. But of course, if you care about understanding sort of large-scale coarse-grained properties, you don't need to do that. It's a lot easier, and the chaos actually makes it easier for you to study the coarse-grained behavior, because you can just replace any complex thing that's happening locally with just a purely random thing, right? So the idea is anything that looks very complicated is essentially a random process. That's the intuition that allows you to get this great simplification and allows us to talk about fluids flowing through a pipe without like solving classical physics for 10 to the 23 particles. Right. If you try and ask the same question about quantum mechanics, there's sort of a second axis, which is the temperature or the energy density above the ground state, and that sets how much entanglement you have to deal with. If you're dealing with correlation functions near the ground state, very likely, this is not proved, but very likely in almost all cases, this is an easy calculation for a tensor network method, even in higher dimensions. But on the other hand, if you want to do something up here in this corner, like compute the exact probability distribution over bit string outcomes for a random quantum circuit that I pull out of my random circuit generator, that's about as definitely hard as anything is definitely known to be hard in quantum computing. On the other hand, what about things like local observables at high temperature? Right? Are they simple to describe, or are they complicated? And so the basic idea of why they might be simple is once again that systems thermalize. That's to say that high temperature dynamics is complex and chaotic, and because it's so chaotic, the state that you start out with becomes very quickly just a completely random state in that sector of, let's say, charge and energy. It's everything that's a conservation law doesn't change. Everything's not a conservation law, it just gets randomized. And if you apply this principle of thermalization locally, it also tells you a system approaches thermal equilibrium. And the physics of that is the physics of hydrodynamics. You say, okay, locally in this patch, you chop the system up into patches, and you say each patch has a local temperature and local chemical potential, and over time all that happens is that these local variables evolve, and they evolve by something that looks, for example, like a diffusion equation, but more generally you can write down what kinds of things are allowed to happen by doing gradient expansion. Right, so this works classically, and the ansatz for quantum systems is very much the same. The key point is that you end up with a classical theory either way, regardless of what your microscopics was. Why is that? So a simple intuition for this It's a bit of an oversimplified cartoon, but you think about one particle in an interacting system, and as the particle moves around, it sort of interacts, it scatters off the others, and among other things, it picks up a random phase depending what other particles it saw, right? So if you like, the density matrix ends up, each trajectory for frozen background particles looks something like this. There's a bra and a ket. And so once you sort of perform the trace over all the other particles, what you find is that only trajectories where these phases approximately cancel survive, and those are trajectories where the bra and the ket are kind of glued to each other. And that means that you can think about the problem about the system not having a bra and a ket, but just having a classical probability distribution over where the particle is. So that's the idea, and so it seems very reasonable that like the rest of the system does this thing where it glues the bra and the ket together. So in some sense, it acts as a heat bath for my individual degree of freedom, and this suggests sort of a very intuitive way of making your simulations a lot simpler. You say, okay, system is acting as its own bath, so let's couple it to some additional external bath, which is some kind of classical noise source, some kind of quantum bath at some high temperature, and so the computer scientists have proved that that doing this makes simulation easy. So the idea would be you simulate your noisy quantum dynamics and then you extrapolate to zero noise, right? And the expectation might be that in a chaotic system, this extrapolation to zero noise doesn't really do a whole lot, because what your noisy correlation function, a spectral function is, it's a blob, but then it remains a blob as all the noise is doing is taking each spectral line and sort of broadening it out a bit. So it's convolving the original spectral function with some like narrow noise kernel. The original spectral function was kind of a broad blob. It doesn't do anything to convolve it with a Gaussian or Lorentzian or whatever. Another way to say this is in the time domain, your correlation function is already decayed to zero a long time before the noise has time to do anything. Right, so the noise is barely doing anything at all except to make your simulation a lot easier. So that's an intuition that, and the intuition you might have based on this is that the noisy and the noiseless system behave in more or less the same way as far as physical observables go, and this works actually for the asymptotics of various things. So if you consider systems with no conservation laws, just a Floquet system or a circuit with no time translation symmetry at all, then what you find is that, indeed, the correlation functions decay exponentially, and the noise just very slightly changes the rate of that exponential decay. There's nothing else to happen, things are going to decay exponentially. That's not surprising. Another important thing is that if you're looking at a system with, say, conserved energy and charge, but no other symmetries, then what you're going to find is that the diffusion constant or conductivity or something is again going to evolve smoothly with noise if the noise doesn't break any important symmetries.
So you don't count time translational invariances.
Yeah, so I mean, if you're interested very specifically in energy transport, and you care about that, then you might have to worry about this. But yeah, even there, if you define a conductivity appropriately, you can still extrapolate it. But yeah, that's right. I'm thinking mostly about charge, for example, in this talk. Right. So, you might think, okay, these are two extreme cases. Well, so in a chaotic system at high temperature, is everything going to look more or less incoherent and classical? Is it going to look more or less the same between the noisy system and the noiseless system? And so my main message is going to be that there's at least one very simple natural object, which is the single particle Green's function, the system with charge conservation that has asymptotically different decay in the isolated system and the system that's coupled to noise, even if the noise respects the symmetry. Okay, that's going to be that's going to be the conclusion. And I'm going to walk you through why that arises. Okay, so once again, I sort of already talked a little bit about this, but in the noise, if you like, the rest of the system acts as the bath for any individual part of the system. And then you have this classical description. The classical description is hydrodynamics. So in order to write down hydrodynamics, just identify the conservation laws. And the conservation laws, of course, obey, they obey a diffusion equation or something like that. So they behave in general as power laws. They decay as power laws of time. In a generic many body system, and less known but also true fact is that pretty much any simple operator like current also decays, also gets infected by these power laws. And that's the theory of hydrodynamic long time tails. So anything that, if you like, the picture is that the operators form a Hilbert space, and so under time evolution, what happens is that something like the current ends up getting mixed in with operators like gradients of the charge, and the charge is decaying as a power law. So this guy also decays as a power law, typically with a different exponent. So in general, everything or most simple objects behave in this way with long time tails. So they all decay as power laws, and these power laws are governed by the hydrodynamic theory, so they don't care about classical versus quantum. They extrapolate nicely to zero noise. Yeah. Yes. Yeah, I'm assuming that the noise preserves the symmetry right now in a strong way. Yeah, I guess that was Matt's question. So it is possible that, so with energy, we don't know how to like implement, anything that's like noise that respects energy as strong symmetry. That's probably somewhat fundamental. But I don't know if it has any interesting consequences in terms of, beyond the question of does this particular approach work? But it's a good question. Right. And so, okay, so what kinds of objects don't just end up being infected by hydrodynamics? One way to think about the way that operators mix in with a charge and its derivatives is that there are two types of operators in a system of charge conservation. There's operators that have the same number of raising and lowering pieces, like C dagger C. That kind of operator includes the charge, the current, derivatives, the charge, derivatives of the current, and everything that starts out with the same number of creation and annihilation operators under time evolution respects that property, right? You're not going to change the number of creation versus annihilation operators. You might create more of both. Like C dagger C can go to C dagger C C, but it can't go to C dagger under charge conserving dynamics. And so that's sort of so in terms of the operator evolution, that means that your space of operators is kind of block diagonal. It breaks up into a bunch of subspaces, and each subspace is characterized by a difference between the number of creation and annihilation operators. So the simplest example of a mode that doesn't that cannot mix with the hydrodynamic modes, it's sort of totally in a different sector of the operator space, is simply the creation operator, right? Because no matter what you do under time evolution, it's going to have one more C dagger than it has a C. And so this object is not affected directly by hydrodynamics. And so in terms of this cartoon picture, the point is that the operator that, the process by which you compute a correlation function like this is, you imagine on one side of, on either the bra or the ket side, you insert a particle and you pull it out at the end of the experiment, right? That's what it means. That's what this expression means if you read it literally. And so, what does that mean? Well, it means that your ket side and bra side time evolution cannot cancel each other out because they have different numbers of world lines in them, and this world line has no partner, right? So it can't cancel. Nothing can cancel it out, and so the idea you might have is, okay, fine. So in that case, this object is going to dephase rapidly in time because the phase accumulated by this guy has no trajectories at all in which it's alive. So naively, you'd expect that correlation functions like this decay exponentially. You expect that you're if you like thinking in frequency space, you would expect that that this guy is just going to be a Lorentzian or something like that. Okay, right. And in fact, that's not true. And the reason it's not true is a slightly subtle one, which is that even if you take a high temperature state, you can think about a high temperature state, infinite temperature state, in fact, as being sort of an ensemble of all possible product states you could write down. And so some of these product states, just by chance, are going to have a long string of empty sites around where you inserted the operator. probabilistically this can happen. We're going to call these regions voids. And so if you compute the correlation function, the key idea is the correlation function has two pieces. You can sort of make that explicit by dividing the density matrix into a set of configurations with a void centered at the position where I'm measuring this correlation function, that's x, and then everything else. And so everything else is going to like probably give us exponential decay. I'm not going to consider that. The point is that the contribution from voids is a lower bound on the decay of the correlator, because these are some subset of configurations. They give you some contributions to the decay. And so basically the question is, yeah, so what is the contribution? So first of all, the voids of all sizes. What's the contribution to voids of what are the dominant size, and what do voids of that dominant size do to the correlation function? Okay, so that's the question. And so now here the key point is that if I'm inside a void, I've created, let's say, I put in a creation operator. It's like creating a single particle above the vacuum. That single particle is not going to dephase, right? It's got nothing to dephase with. It's gonna just sort of rattle around inside the void until the void fills in. And while it's sort of sitting inside the void, it's not, it's gonna decay, let's say, as a power law, and eventually the void's gonna fill in. And the correlation function is going to decay. The bigger the void is, the longer the correlation function survives, but the smaller the contribution was anyway, because those voids like super rare. So there's some kind of trade-off between these two effects. Okay, and so I won't bore you with this, but the idea is that you capture this with a simple model where essentially what you do is you add a small decay term to the Heisenberg evolution of an operator, which says that anytime my single particle that I inserted collides with any other particle, it gets entangled with it, and let's say entanglement never becomes a single particle again, never comes back into single particle sector, it just decays. It's just gone forever. And so, and that says that the operator is going to decay at a rate that depends on the time-dependent density of everything else. And to figure out what that time-dependent density is, you can just go compute that within hydrodynamics. And there are two cases. So one case is the case where we actually have like a rigorous result, and that's in random circuits. In random circuits, there are no symmetries or conservation laws other than the charge conservation that I put into my definition of what the gates are. And in that case, the key point is that in a random circuit, and this is what's unrealistic, the diffusion constant remains finite even at zero density, right? And that's because the evolution is time dependent. There's no Bloch's theorem. And so in that case, it's very simple to estimate that if I have a void of size L, it'll live to a time that's L squared over the diffusion constant some number of order 1. Okay? So in that case, the argument's very simple, which is that dephasing doesn't set in until the void is filled in. A void of size L fills in on a timescale of size L squared. So you fix T, and then you ask, well, what are the dominant voids? Dominant voids are voids of size square root of T, which have just about not filled in. And so their contribution, their probability is e to the minus square root of T. And their contributions, the correlation function, is some power law thing that's a prefactor. So the correlation function decays to leading order as e to the minus square root of T for the single particle Green's function in the case where you're looking at this random dynamics. Okay, and that agrees. So in this case, they're saying you're able to compute various things using this effective stat-mech description of random circuits. And so numerics are very pretty in a way they're not going to be in what I show you next. Okay. Do you have a question, Veer? No, because at any given time, I can find a big enough void. Right? And so this is always slower than the exponential.
So that global exponential phase actually.
Yeah. There is no exponential regime. It's always a stretched exponential. It's always e to the minus square root of T. Because at any given time, you can always find a void that's big enough. And it's just not rare enough for its rareness to win. It's like it's always just about common enough to dominate the correlation function. Yeah.
Prefactor can be very small.
Yeah, the prefactor is, I mean, again, like, yeah, that's why I had to do the numerics, right? So yeah, the prefactor is whatever it is that plot. Yeah, but I agree. It could have been worse. But in general, yeah, there's no particular, the prefactor is really just the decay of the single particle Green's function above vacuum. But we know what that is, and it's not like it's 1 over t to some power.
Longer time to see this than
Yeah.
shorter time.
Yeah, exactly. Yep. Yeah, exactly. The square root always wins, and yeah, it seems to win, pretty fast, right, on this curve. So it's like, so this is times of order, like, I don't know, so 4 squared is 16. So these are times where like you'd comfortably see an experiment in this model. Yeah. Go ahead, Matt.
Sorry.
Yeah.
No. Is this related to having to have a finite on-site Hilbert space? Or
Yes.
like what?
Yes.
Okay.
Yeah. It does require
Because
that.
if I take a CFT
Yeah.
for like my
Yeah.
fermion with fractionalization and I calculate the
Yeah.
correlation function at finite temperature, I always
Yeah.
get exponential.
That's correct. And so that's because, I mean, so yeah, I've been asked, you can think about this in your liquid, right? And the point is linearization is what screws you. Because in fact, there's always a bottom of the dispersion. It's just, you've just removed it from your theory, but it's always there. Yeah.
I see.
But that's what's happening here. Yeah. Okay. So that's the random circuit case. But then now you can ask, well, what about if you have a translation invariant Hamiltonian? Your space and time translation invariant, nothing's really changing. And in that case, the thing that changes relative to the previous slide is the diffusion constant blows up at low density because, at 0 density, the excitation is just block states, right? So they just move ballistic. So the thing I insert just propagates out ballistically. Right. And so you can convince yourself that the diffusion constant in general is going to scale as 1 over the density at low density. This is because the dominant channel for relaxing this guy is via like a 2-particle Umklapp scattering process. And so now what you can do is you can say, okay, fine. So I'm going to do the same problem as before. I have my region with a void in my initial state, and I ask how long it takes the void to fill in. But now I've got to ask this question with this funny diffusion equation with the density-dependent diffusion constant that blows up at low density. Okay. And I can just go ahead and solve this. I guess a lot is known about this kind of equation in the literature. And what you find is that the leading behavior of the density near the origin is that it's got this T over L squared, then and then it kind of grows parabolically away from there. Okay, there's some exact form which I don't think we know in closed form, but like this is the sort of behavior near the place where I inserted, near the center of the void, which is where I inserted my operator initially. Okay, so that's this guy, and now I just go ahead and plug it into my Hamiltonian. And so what I do is I say that so one more thing is that I expect that in general what I'm doing when I hit the void with a creation operator is I'm inserting a magnon or some kind of excitation with some particular momentum. And I would expect that the longest lived ones, the ones with the smallest group velocities, so without really loss of generality, you can expand the dispersion around k equals 0 and becomes quadratic. And go ahead and like solve this problem because it's an oscillator. It's a particle in an imaginary harmonic oscillator, and you just go ahead and bang out the eigenmodes of it. The key thing I wanted to say is that is sort of the punchline. You don't need to worry about this guy. Just look at the overall decay rate that scales the central density. Central density grows as T over L squared. And so a void of size L gives you contribution that's like, first of all, it gives you, it's exponentially rare in its length. That's this factor. And then it also has a decay rate. It's got a persistence time that scales this way, right? The central density times time. And so now you just optimize this by saddle point, and you find that the correlation function in general in these systems is supposed to decay as e to the minus t to the 2/3. And this e to the minus t to the 2/3 is consistent with numerics we've done in a wide variety of systems that have charge conservation. We found, it's all finite size numerics and it's not out to super late times. So you find some where the exponent's more like 0.61 and somewhere it's more like 0.7, but they're all kind of ballpark, they're all ballpark 2/3. So it seems like a very generic behavior for this class of operators in a system with conservation laws. Okay, and you can see immediately that this effect is unstable if you add noise, because what happens if So I was talking about the envelope, right, which is this guy, but of course inside the envelope, the time evolution of this object also involves the accumulation of phase. And that phase accumulation is in general going to be some complicated thing. Depends the precise details of what the time evolution is. And what happens basically is that once you introduce any external noise, even one that conserves the symmetry, you dephase all those oscillations, and you get a nice exponential decay. So the moment you have noise, the stretched exponential goes away, you get a regular exponential, and if the noise is weak enough, there's a crossover timescale separating the sort of coherent and incoherent behavior. And so that's rather straightforward to estimate. The way I like to think about it is that, system acts its own bath, but the caveat you need to that statement is the bath has holes in it where it's not acting. Whereas if you couple in an external bath, the bath is acting everywhere, and that's why these two scenarios are like fundamentally different. And so these guys give you, quite generally this e to the minus g to the 2/3, which is in some peculiar, it's a very strange quantum coherence effect that persists in one dimension, even at infinite temperature. I'm not going to talk about this, but you can make this a bit more rigorous using random circuit technology, at least in the random circuit case. So let me just conclude. So so you see these signatures of quantum coherence, and so these two exponents that depend only on whether diffusion constant diverges at low density or not. And so it'd be interesting to test this in experiment. I didn't have time to talk about the other, because when I was asked to give this talk, I wasn't told how long it was going to be. So I had an entire other part which I'm not even going to talk about, except to mention, to advertise this result that we found a family of systems in which diffusion constant is a discontinuous function of noise. So it has one value when the noise is on, and a totally different value that's off by order one when the noise is turned off. So, but that's I'm not going to talk about that anymore. So I'm going to stop here and take questions.
Question?
Yeah, go ahead, Andrew. Yes.
You probably know the results when people look at multipole, let's say dipole constellation
Uh-huh.
rules.
Yeah.
Generally get something.
That's right.
The number
Yeah.
of derivatives you get in your
Absolutely,
question
yes. Yeah.
goes like
Yep.
the four zones.
Yeah.
Would that still fit into your general description, or would it have the same?
Yeah. So even in that case, you would have this mechanism. It'd give you a different exponent, obviously, because like all the, there are different powers of everything. But it would also have the same phenomenon. And in fact, the good thing about that is this effect is basically it's strongest in one dimension, because it's just like hardest to fill in a hole in one dimension. You got to come in from the edges. But if I wanted to see the same effect in two dimensions, I could do that with charge and dipole conservation.
And then instead of 2/3, it would have just a different power.
Yeah, it'd be a different power. I don't know off the top of my head where it is, but it's easy enough to compute. Yeah.
So what is the scope of this breakdown? Because as you know, there's this detailed fluctuating hydrodynamics, classical and harmonic chains.
That's right.
Is that impossible?
Well, I mean, what do you mean by is that impossible?
Does that also have this discontinuity?
You mean, are you talking about the result that I was actually talking about, the one that I advertised up there? Because the one that I advertised up there in gray is a nonlinear fluctuating hydro result.
So, okay, I guess I'm asking, is nonlinear fluctuating hydro doomed in one dimension because of what you said?
No, I don't think so. I think that nonlinear fluctuating hydro is a theory of a different block of the operator space. It's the theory of the block where there's the same number of creation annihilation operators, and there like everything works more or less as you'd expect. And the nonlinear, there are some effects like this, but there's some leading to the nonlinear hydro.
But then how do you get to discontinuity in fusion?
Oh yeah, that happens. I didn't tell you anything about that, but it happens within nonlinear fluctuating hydrodynamics.
Nice.
It's not, yeah, it's a different result. It's not related to voids. Drew.
What happens at hydrogen?
So 2 dimensions is marginal, where the void contribution and the regular contribution scale the same, except that I think there's an extra multiplicative logarithm, which we haven't worked out in great detail.
But in high enough dimension, I guess the probability.
Yeah, exactly. It's just too rare. Yeah, that's right. So in 1 dimension, it just happens that rare regions that take a long time to fill in are just like not that rare because you got to fill them in from the edges, and there's not that many edges to come from.
So you need to get some like parallel 2 factors.
Yeah, it might even be, sort of e to the minus t over log t or something, but that requires a much more careful calculation than we've actually done, and we had nothing to compare to anyway. So I don't. Yeah, but it could something like it could survive. And like I said in response to Andre, if you did fractons, then this would definitely still exist in 2 dimensions.
Okay, let's take Sarang
Thank
again.